Yeah, hello and welcome. I hope you can hear us well. Maybe you could just give us quick feedback if you can hear us, especially in the last rows. Can you hear us? Good. Perfect.
Great, thank you.
Thank you so much. Yeah, welcome to this lecture today. We are really excited and happy to see you also in person today. So all the following lectures will be held here in the lecture hall P1. But we will record all the lectures and also upload them to YouTube, probably tomorrow.
Yeah, maybe on Fridays, because on Thursdays we have other things to do after the lecture. Yeah. But on Fridays I will cut them together and upload them on YouTube then.
Exactly, yeah. Great. So, what is the topic of today?
Today's topic is all about pointers again. Yeah, we're talking about pointers, and Michi and Julia, took a lot of our content, but I think pointers is such an important topic that it's good to do it once more, and a few new things are definitely also there. So we're talking about pointers, strings, arrays,
functions,
and the combination of all of them. So the pointers on their own are not that hard to understand, in my opinion, but the combination with functions, with strings, with arrays can make it very complicated. So today's lecture is again all about pointers. Yeah.
But before we start with talking about pointers, again, some brief organizational matters. We've already heard it in the practical streams. So practical. Not stream.
It's not a stream anymore.
We
also have to adapt now.
So we are here in week 5. So today there will be again some weekly exercises. Yeah, thank you so much. That belong to assignment 2. Assignment 2 will be released on the next week. You will get informed about that. Again, you will get a repository. And don't forget to do the weekly exercises before the deadline of assignment 2. Otherwise, you will get some deductions if you don't have at least 50% of the weekly exercises done.
And I also hope that most of you, or everybody of you, submitted yesterday assignment 1, so the deadline is already over. Hopefully you submitted that, and now we are ready for assignment 2. So last week's content and today's content is already all you need to know for assignment 2, which will be handed out next week.
Plus the content of the weeks before. But
yeah, of course. Yeah.
Okay, before we start with talking more about pointers, let's do a quick recap. For that, we have prepared a Slido. So please just scan the QR code that is shown here, or visit the website slido.com and join via the code, passcode.
I think this passcode is not necessary. I don't know why it's always listed there. So it should be just going to slido.com and enter this 7-digit code.
Yeah, in the meantime, we could have a look what is shown here. So the code snippet here, it's about arrays, looks like. So we have an array size 5 with 5 numbers in the array. Then we're doing some stuff with the array. So we're creating a local variable with the first element of the array with a for loop.
That's a tricky one.
That's a tricky one, yeah.
So be careful there.
Yeah.
Think about what I is. So it works and it compiles without errors and without warnings.
Hopefully, yeah. It should work, yeah. Yeah, have a close look at the condition, the first for loop, also the value of I. And then there's some assignment at the position 4 of the array, and then again a loop for printing. Okay, let's wait a few more seconds here. So what is the output of this code snippet. It's already quite late and
Yeah.
such a hard task to calculate this. Yeah.
All right. I think we
Yep.
can continue. So
see.
what's the correct answer here?
So most
Yeah.
of you got it right. Perfect.
Congratulations. Yeah.
The correct answer is 2, 3, 4, 5, and 1. Why is this the case? So we store the value of the first element, so 1, in this variable. We have a loop that goes from 0 to 3. And what we do here is we shift all the values from the right to the left. So we start with I0, and we shift the value 2 to the position 1. So the value 2 is at position 1, 3 at position 2, and so on and so on. And after the loop, we assign the value of our original first element, so the value 1, to the last position of the array, so the position 4, or it's the fifth element. And yeah, after that we just print the numbers, and what we see here, we have just shifted the numbers from right to left.
Cool. I think we have another one for you.
It's a tricky one.
A tricky but a very, very short one.
Yeah.
What do you think are the data types of the two variables name1 and name2?
So we've learned last week that this asterisk here, the star, denotes a pointer. So we probably have some kind of pointer here. But are both variables pointers?
So again,
Just one.
it works,
Yeah.
it compiles without errors and without warnings.
Okay, let's wait a few more seconds.
Maybe we should add that, I don't know if you have shown it in the variables lecture, but you can define more variables by just like concatenating them with, like that.
Yeah, so it's a perfectly fine variable declaration of, in this case, 2 variables. You can define 10 variables, how much you want and how many you want. And yeah, but we don't really recommend it to do it this way.
Why?
Okay. We'll see it.
Let's have a look at it.
Yeah?
What's the problem here? Yeah.
Yeah.
It is so. Some of you were tricked, and I also, to be honest, was tricked when Sebastian showed me that before. It is very, very tricky because you would assume that both variables are char pointer, but only the first one is a char pointer.
Yeah.
The second one is just a char.
The second one is just a variable with the data type character. If you would want to have a character pointer also for this variable here, we would have to add the asterisk somewhere between the comma and the beginning of the identifier here to know that this is also a character pointer, not only a character.
So be aware, if you do something like that, always think of this pitfall. Now most of you know it, so 58% of you know it, so no big deal.
Okay.
All right, let's continue. And I thought of a use case of pointers in real life. So maybe you're thinking, why should we use pointers? Why should we learn pointers? What is a real life use case for that? And I came up with Spotify. I think most of you know or use Spotify. Has about 600 million users, about 600 million different songs. And I looked it up yesterday, about 4 billion playlists with an average of about 100 songs in it. So that's a lot of songs and a lot of playlists and a lot of users. So we could assume like there are the playlists and there are different playlists like my favorites, summer playlist, whatever, and there are just the songs stored. So 4 billion playlists having each 100 songs stored. would be one implementation, one type of implementation. So we can come up with the question, Spotify stores 400 billion songs, so for each playlist, the 100 songs. And luckily, I hope they don't, because I would then suggest that you should use a database. So you just use one database, every song is stored once inside, and then you have each playlist. So there are the playlists, but the playlist content is just a pointer, so also sometimes called a reference, to the actual songs in the database. So now you reduce your memory consumption from each song, which is like about, 10 megabytes, to just pointers, and you have to store each song only once, and the pointer is just 8 bytes. So for each playlist and for each song in the playlist, you save a lot of memory, reducing from 10 megabytes to 8 bytes. This is just one example where you can use pointers because you only have the element once and you need it only once, because none of the users will ever make a change to the song. The song still remains always the same, but every user wants to access it. So everybody gets a pointer to it, and it's always the same song.
It just came to my mind, if one song, let's say, gets removed for copyright issues, whatever, it would be quite a lot of effort to remove it from
all the playlists. Yeah, that's another benefit. Yeah, so if you want to modify the song, you can modify it, and it's modified indirectly or directly in all the playlists. Everybody uses it. Yeah.
So it's great to have some kind of pointers here.
So hope that was a little bit of motivation why pointers are important. There is another thing I want to add here, because you submitted the first assignment and maybe also had something like that. Hopefully not that intensive, but like infinite numbers of if, else, for loops, nested, whatever. And this is very, very hard to read for us, hopefully also for you and for the tutors. So we somehow want to avoid it. And this is, by the way, the only topic today where it's not about pointers. This is about how we can write code in general to reduce this amount of nesting. But before that, let's see an own small problem. We have a function called print grade, and we want to print out the grade of a specific point range. So let's say we have this function, it takes the points. And first we want to say, okay, if the points are greater than 0 or the points are smaller than 100, then it's valid because it's in the range from 0 to 100. Otherwise, it's a wrong input, so we print out wrong range and return -1 in this case. And here in this section, it is valid user input, so we can come up with, okay, if the points are greater than 88 points, then we know it's sehr gut in German. All the other grades then fall into this else branch, and we can continue here in this else. If the points are greater than 75, then it's good. Then otherwise we fall again in this else branch, and you see it, so we can go in this else branch again. It's befriedigend, and otherwise we fall in this else branch again, and so on. So it can get very, very hard to read, and even for a very simple thing like that, I know it's a bit blown up. You can make it a lot of easier, but I just want to show you that we sometimes or unluckily often see constructs like that. So we just want to make you aware that there is a solution and a better writing option for nested things like that. Yes? It's just for no reason. You can return whatever. I think initially my thought was we return the grades 1, 2, 3, 4, 5, and -1 is just like an error code. which then when I want to call this function, I know, okay, something went wrong, but no real reason in this case. All right, yeah, I hope most of you do not fall into this part, but sometimes it can happen. Okay, how can we improve that? We can use something that's called guard clause, and this is an integrity check and a precondition. It is like a pattern to remove nested complex control structures. How does this work? So, okay, instead of having this in the beginning, where we ask the user for a valid range and all the invalid range is in the else clause here, we can switch it and say, okay, if the points are smaller than 0 or the points are higher than 100, then we have the wrong range and we return from the function immediately. The cool thing with this is when we come to this line here, we know that this is a valid user input. Oh, it's a typo here. It should be valid user input. Sorry for that. So when we are here, we know that it's valid user input and we can continue here. We don't need an else branch because when the if is true, it already returns inside the if. And then we can ask again, if the points are greater than 88, then print. Sehr gut. We could also get rid of this else by returning again here and have all the other grades afterwards again. And we can do it again for the next grade, and we can do it again for the next one. Make it a bit smaller for the 4 and for the 5. So when we end up here in this line of code, I hope that was not a beer can. When we end up with this line of code here, we already know, okay, every of this condition above is not true, so we can print nicht genügend in this case and return the function. So this is before, this is afterwards, applying these concepts, and at least in my opinion, it's much more readable. Much
Cleaner.
Better to understand, because sometimes when you want to modify like the if-else clause here, it's hard to comprehend when exactly do I come into this if-else, else section. So it's very hard to understand. But if you write it like this, it's very easy because this all just have to be false and then I'm coming to this section. It's much easier for us to comprehend and to follow this path. So I would suggest if you write a function, before you write it, just think of excluding all the wrong paths. Yeah. So this guard clause is to end functions early when a condition is met. So instead of focusing on the correct program path we have seen here in the beginning and always having the correct one in the if statement, we can instead exclude the wrong program path in the beginning, and maybe there are more than just one. So remove all the program paths, the executions where there is wrong user input, and then you know, okay, you can deal with only correct input, and it works pretty well then.
But as I said, you can have one wrong program path, you can have two or multiple wrong program paths. For instance, if you want to return a different integer value, depending if the points are less than 0 or greater than 100, you could just have two if guard clauses. So you can have one guard clause, you can have multiple guard clauses. Depends on the program, what is defined.
All right. There is a second way to tackle this problem, which is a very easy one, in my opinion. It's just using functions. So what we also could have done is, in our print grade function, if this condition is met, we just call a function Of course, in this function, we still have these nested statements, but for us, it's then easier. So when this function here works, and we know that it works, we have tested it once, then we just came to this function again and read, okay, if this statement is true, we calculate a valid grade. Okay, so we have a meaningful name, we know what this function does, and it's easier for us to comprehend what this if statement is about. And of course, it again would be easier if you also resolve this nesting here, but using functions is once again a very powerful tool to make code more readable.
And reusable.
And reusable, of course, yeah. All right, this was our
short
excursion to, not pointers, but
we're getting back to pointers. And let's say arrays, but it's also pointers. So, we talked about arrays last week, and you are probably familiar with this line here. So, just declaring and initializing an array, in this case with the length 5 and the values here. So the first step in this example is, what is the size of the array if we have it like that? We'll see it soon. And then we want to print the size again. So we would expect to have the same size if we do it here and here, right?
Yeah.
So we pass the array to the function print size and do the exact same thing as we do here. And now we want to know the output. So what is the size of the array in both cases? Does anyone have an idea what could be the output here?
So now we're talking about this line here first.
First this line.
This size of numbers, what is the output of this one?
Yes.
5, okay. Any other guesses?
Yeah, let's get some guesses. We have 5. Yep.
Yes? 8, okay.
8. So for the first printf or for the second? So for this one or for this one? Or for both?
Both the same,
both the same?
Yes?
The second one would just be the size of the points of both numbers.
Okay, yeah. Let's have a look at it.
Let's have a look at it. The first one is 20. Why is it 20? We would expect it to be maybe 5, 8, whatever.
5 would make sense because we have an array of 5 elements inside.
Yeah.
But they're integers.
Integers, yeah.
So we have to calculate the 4 bytes for the integers times 5. 4 times 5 is 20. So the size of the array is 20 bytes. Remember that size of always gives us the bytes of the consumed bytes, in this case of the array.
So with your integer value with a size of 4 bytes, again 4 bytes and so on, so 5 times 4 bytes, this is then 20. But why is the second output 8? We've already heard it. It's the size of a pointer.
Yeah.
So,
but you're declaring here again an integer numbers array with a size 5.
That's actually what Michi and Julia said just before. So we can denote it as an array here. But internally it's actually a pointer. So it's just some kind of syntactic sugar, I would say, to use the notation as an array. But actually it's a pointer we pass to this function. And therefore, the size of the pointer is then 8 because, the size of pointer is 8 bytes and it points to the address of the first element in the array. So we have it here. Yeah.
There is also one implication of this. So as soon as you hand over an array to a function, you are losing information because you're losing the information of the size. It's always only 8 bytes because it's just a pointer to the first element. So what you usually need is a second argument, a second parameter, handing over the size, because otherwise for you it's not really possible to determine the size of this array.
That's
Even
true.
though it's written there, this is just because we know it the hard-coded way.
Yeah.
But when you don't know it, it's impossible to find out. So that's why most of the time when you hand over an array, you need a second parameter with the size of the array.
Yeah, otherwise you simply don't know and
Yeah.
can't calculate the size of the array. That's a very good point, thank you. Okay, yeah, we've already heard about that today. Returning a local array variable. So we have a function called here, and we want to create an array and return this array back to the main function. We've heard about it, we shouldn't do that.
In the practicals, yeah.
Yeah, we shouldn't do that. We must not do that actually. But why is this the case? The full explanation will be discussed next week.
I think next week when we talk about memory in detail, yeah.
But yeah, for today, each function has its own memory space or memory area. So the function here has its own memory area, and once we execute the computer executes the return array statement, this memory area is gone. We cannot access it. We simply don't know what happens, and we're not allowed to access it anymore. So if you would want to access the array that is returned, so the local array that is returned to the main function, we would get some strange error message. It's most likely SIGSEG, so
Yeah.
segmentation violation, or we just call it segmentation fault. And yeah, this isn't good at all.
Yeah, and the program then ends with the exit code, I think 137.
Yeah, I think
So this is also an indicator that you accessed memory that you shouldn't have accessed, because it's maybe an array where the memory is not anymore accessible for you. So there is something terribly wrong in your program, and this also often results in a so-called segmentation fault.
So just for explanation, we create a local variable here, we return it, but then the variable goes out of scope because the function ends and the memory area is not accessible anymore. We are not allowed to access it. We can, but most likely will be a segmentation fault, and that's why we can't work with the address that is returned here in the main function.
And unfortunately, our lecture ends here, because there are lectures in the third and fourth semester where you deliberately want to exit memory that is not your own. So there are possibilities and there are ways to do that, but this is more than security issues, and there is a dedicated lecture for that. So be patient if you're interested in that. There are lectures doing explicitly just that.
Yeah. But for this course, it's sufficient to know that you can't access an array that was created locally in another function. Okay, so please don't do that in the practicals. And now we have talked about fixed length arrays, so we always, or most of the time, had a constant expression in the definition of the size of the array, but we could also use a variable to define the length of an array. So instead of writing here some constant expression, for instance, a literal constant or a constant defined by a define, you could use a variable. However, it is not really variable in that sense that you can add as many numbers in this case you want, but you can define the size as a variable. So once you have defined the size here, the size of the array is always the same after that. So it's really just the definition of the size here in these brackets.
So if you afterwards change the length variable, let's say increment by 1 or increment by 10, the array stays the same.
Exactly, the size of the array stays the same when it was declared here. Yeah.
So, you see, C is much more restricted than, for example, Python or other languages. You have to be more careful. In Python, it's basically up to you how long it is, and it can be extended or appended wherever you want. It's much harder in C, so we will also learn next week how you can make arrays bigger. It's not that easy, but yeah, we will talk about it when we talk about dynamic memory.
Yeah, but when we're talking about memory, so maybe just as a some kind of teaser for next week, this variable here is stored on the stack, in this case of the main function. And we will learn next week about other places in the memory where we could store variables. Okay, then.
Yeah, strings again. Wow. Yes, a question.
Yeah. So the question was
This case?
Yeah, exactly.
Yeah.
I think you meant this here. Yeah. So this is just a mathematical operator, 5 times size of int.
Yeah. Yeah.
And yeah.
Yeah.
Exactly. Okay, let's go back to
Any other questions?
strings. Yes.
Yes.
Can you get one slide? Yeah, exactly here. Can you hear me?
Yes.
Because I think there is a similar exercise on the line.
Could be, yeah. Yeah, I think so.
I think so, yeah.
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 I've already tried it, and I think I have tried it like this to make the array the size of the user input. But for me, it didn't work, and I think I have the same code as here.
So did you just declare this variable as it is here declared?
Yeah, the array.
The array. Maybe you can have a look afterwards.
I haven't tried it on OnlineGDP. Have you?
I think it should work.
It should work.
It
Okay.
should work.
Yeah. So we can have a look at it afterwards
Yeah.
if you want. Yeah.
Okay, any other questions?
Or if it's just about OnlineGDP, you could also ask on Discord. Maybe not your submission, but just write a few lines of code and ask there, and we will be happy to answer it there.
Okay.
All right, then continue with strings again. We already know some data types. We know the Boolean, characters, integers, long floats, doubles. And we also have heard last time, and also in the practicals, the date or the size of a string is basically for us a bit dubious because it's not clearly defined. It highly depends on the number of characters that are in the strings. So what's the size of a string? When we declare it like this and then print out size of string, we came out with 6, because we have the 5 characters and then we need the null byte in the end. So always consider the null byte. I think Mich and Julia also showed that in the practicals before. Strings have, of course, also an address. And if you print it like this with a %p, then you get back the address of the first element. And this looks very familiar because we already know it from the pointers where we had it like this, where we have an address and store it into the pointer and then just print out the pointer here and we get out an address. So what we know now is arrays, or in this case strings, but strings is just a special case of arrays. Arrays are similar to pointers.
And just to clarify, we don't need the address of operator.
Yeah.
So we just use the variable and print a, in this case with %p, the address of the variable.
And here on the right, it's basically the same. Not really, there are a few differences, but it is pretty much the same. You can also declare the same string with a char pointer, and when you then print it out, you also get back the address when you print it with %p. So you can see now that there are very much similarities between an array, and a string in this case, and this pointer here. But there are a few differences, and they're very important. First, we also saw that when we have the size of an array, in this case it's 6, because 5 characters, 1 null byte, And this is also implicitly included when you write it like that. At the pointer, when you declare it like this, the size of it is 8. Why? Because it does not consider the number of characters inside the string. So the string can be 20, 50, whatever long. It only counts that the 8-byte of the pointer. So basically what the address needs. So this is a huge difference. There are a few others. So on the left side, again, we have this string declaration, on the right side, the pointer declaration. This on the left side is really an array. This on the right side is a pointer to the first character. On the left side, and this is maybe the most important one, this can be modified because it's an array that is stored on the stack of the current function. The right one here is a pointer, but only the pointer is stored on the stack. So you can modify basically the pointer, but it points somewhere in the memory to a location that you cannot modify. So that's very important. If you want to access or let's say modify one of these characters here, it's not possible. Your program will crash because you are not allowed to access this one. But you're allowed to access, so access is wrong, sorry, to modify. You're allowed to modify these characters here. So this is a huge difference when you declare a string. And it's also, as a short hint, very, very often occurs at the exams. So would be good to have a look at it before the exams.
And so this means we cannot just say my hello is, let's say, bye, whatever. So we cannot just reassign a value. So this is not possible because, we would get some error message.
Yeah. And of course, as I said before, the size here is always 8-byte because it's just a pointer. And the size on the left side is depending on the number of characters inside the string. In this case, it's 6 because 4 characters and then the null byte in the end. Yeah, a short quiz for you again. Should be the same Slido. What do you think is the output here?
Maybe as a hint, have a close look at the declaration of the variable myString. So what's the data type here? Okay, let's wait a few more seconds. So what we do in the loop is just printing character by character, and I goes from 0 to the size of my string minus 1. So what is printed here?
I think it is a short example from one of the previous exams, so not from the last year, but I think from 2 or 3 years. All right, let's have a look at it.
Have a look. Let's see what.
Yes.
Perfect.
Great. Okay. So we explained it in a good way. Great. The pitfall here is indeed that we have a pointer here. Pointer is always 8-byte. So this I variable only counts until 8, or in this case, until it's as long as it is less than 8. So in this case, we only count for 0, 1, 2, 3, 4, 5, 6, 7. This is why only the first 8 characters are printed, and then it just stops because the loop stops even though the string would
Actually,
have more characters, yeah, but the loop stops here.
Yeah, great. Most of you got it right, so that's really good.
Should we end now?
We could.
No, we have a bit left, and yeah, let's see. So we know from the data types now, strings have 1 byte per character, include plus the null byte. And we also know, but please remember that pointers always have 8 bytes.
On a 64-bit system.
On a 64-bit
But
system, but we
yeah.
assume that we are also always working on a 64-bit system. Yeah, correct. Yeah. Any questions to this?
Yes.
Spaces. Spaces are just on the ASCII table another character. It's regardless what character it is just a number. If you convert it in the ASCII table, it's just a number. I don't know what's the space ASCII
I don't know.
number, but it's basically stored as it is every other letter or character. It's just a number under the hood. And it is like interpreted as space then.
Yeah. You could just look it up in any ASCII table.
Yeah.
You find on the internet or wherever. Yeah, it's just one single character.
But that's a good question because some people always think that the null byte is just a space because it's kind of empty. It's not. The null byte is really just the value 0, which means it's the end of the string. Yeah, but the white space is not on ASCII table 0. It's just, I don't know, I think it's 69 or something like that. And yeah, so the null byte is just on the ASCII table. You see when you go to the null, there it's really stand there, that's the null byte. So that's basically the end. Yes?
Does it mean that we can terminate the strings with only like an integer value of 0?
Yes, that's a good question or just a good comment.
Maybe just repeat it also for
thank you.
recording.
The statement is, can we just AND strings by just adding a null inside, a null byte inside? Is that correct? Yes.
Also using the integer value 0.
You can do it when you use the integer value. You cannot do it when you add the character null. Because the character null gets converted to an integer value, which is, I don't know, again, something between 60 and 90. This will not end the string, but if you really write the integer value 0, this means that the string will end there. And that's how you also can modify strings and cut them somewhere in between. For example, if you just add, let's say, string at number 5 is 0, and then you print it out, you will see that it ends, it only prints the first 5 or 4 characters.
That's a very good question, yeah. Any other questions?
Okay, then let's continue with arrays and pointers, but now we want to know how we can access the elements.
Yeah.
There are different ways to do that.
There are different ways. So we have already learned one way to access elements. It's just by using the index operator. So we say variable, then these brackets here, and inside the brackets we use the position, the index. So if you want to access the first element, so at position 0, we can just say data at the position 0, and in this case we know it's 90. We can do this for the second element, so at position 1, and so on. We've already learned it. But now before we actually use pointer arithmetic, we will have a look at the memory. So what happens here? Our first element, so 90 in this case, is stored at the first address in the memory. Let's say it's the address 0x0, or 0x3 in this case actually. So if we access this value 90 by using the index operator at the position 0, we access the value that is stored at this address here. what happens if we access the second element? So if we use 1 instead of 0 here, we access the element that is stored at the address 0x4 and 0x3. This goes on till the end of the array in this case, and yeah, this is quite convenient to use.
Why do we have 4 of this? Cells in this case?
The cells?
Yeah.
Because these are the bytes. It's not actually, how many bytes are there? It's 4.
It's 4,
So
yeah,
4
because
bytes,
we have
yeah.
integers.
4 bytes, exactly.
Yeah.
So
So we could store a larger number here, but all the higher numbers are just 0 because we only have stored the number 90 inside. Yeah, but
Yeah.
basically we have room for storing larger numbers.
if we would have a number that takes up to 4 bytes, we could store it here in this address. But we have just small numbers, so we can store it there. Okay, great. We can use the index operator. What else can we use? Well, this looks strange.
Yeah, because data is an array, and you add 1 to an array.
Yeah, that's what would happen if we would add 1 to an array. That's, looks strange. But we have learned today that every array is actually just, or is the address, and this address is the address of the very first element here. So again, we have, if we just use data, it says we have 0x0. Okay, this is this address here. So if we now say data plus 1, we now have 0x4 and not 0x1. And the reason why it is 0x and 4 is because we add 1 times the size of, in this case, the integer. So we add 1 times 4 bytes. And so we can jump to the next address, to the second element here, just by adding data plus 1. So by adding 4 bytes to the actual address of the first element. And we can do this for the second element by just adding data plus 2. Then we jump to the address 0x0008. And we can do this for all the other elements in the array. We could use data plus 3, data plus 4, and so on. So every time we use data plus then some value, we say data plus the value times the size of the, in this case, integer, the size of the data type.
And we are not adding 1 to the first element or to the second element. We are really adding 4 bytes, in this case, to the pointer, so to say, so to the array. So we have the address. But we will see in the next few slides how we can use it.
So we're kind of modifying actually the address and not really the values here. Okay, so this is called pointer arithmetic. We are adding some value to the array here, to the variable data, which is an array, an integer array. And with that, we can also access elements of the array instead of using the operator, the index operator. And if we now do that in our usual way we have learned so far, is we just write data at the position 1, so the second element, and this is 5. But now we can say data plus 1. So this is the second address of the contiguous block of memory. And in this address, the value 5 is stored. And if we now dereference it using the asterisk or the dereference operator, we also get the value 5. So we can use this line or this line and both result in an output of 5. Maybe we can...
Why should I use the first line? The second one is much easier.
Let's go to the next slide here. There are many use cases.
Yeah.
So for instance, we'll see it next week.
I think so, yeah.
For example.
Next week,
Where you cannot declare and initialize an array in this way anymore. And there, yeah, you're somehow forced, maybe sometimes, to use pointer arithmetic. It's also sometimes quite helpful. And yeah, this is just another way of accessing elements of an array. So this is the same as the index operator. We can just use dereference data, which is 90. We can add 1, so 4 bytes to data and dereference it. This is then the second element, it's 5. We can add 2, so 2 times 4 bytes. And this is 7 when dereferenced, and so on. So we can just use this, let's say, offset of the number of bytes to access elements of an array.
What would happen if I say data plus 8 and dereference it?
It's a good question. We don't know.
We don't know.
We don't know. It's undefined behavior. We could get some number. But
yeah, so we are basically accessing areas, some values somewhere here. Sometimes it would work. Sometimes you crash on runtime because you get a segmentation fault again. So on runtime, the program sees that you're accessing memory that you do not own, and then you get a segmentation fault. But sometimes when you just have one off, so maybe you access this one here, data plus 7, it would maybe work depending on different conditions, but sometimes it works. So still you have to be very careful and do not count too far. So in this case you have this 2, 4, 6, 7 values. If you count and if you want to access the 8 value, you're in troubles because you don't know what's there.
But it's dangerous. It could work. So you could get some value. We don't know which value.
It's very dangerous, and you don't know. Sometimes the values make sense that are there, and sometimes don't. So you have different behavior depending on when or how often you execute it, and this is very, very annoying to find out what's the problem. All right, any questions to this? Because when you understand that this is just a pointer, and you can manipulate the address, adding something to the address, and you could also, if you have the data plus 5 and then you subtract 2 to go back to this value here. So you can manipulate the address just as it is a normal value, and you can work in that range.
As I said, it's really just a manipulation of the address we have. And in this case, it's the address of the first element of the array.
Any questions?
And it's absolutely okay if you don't fully understand it yet. It's really
it took me also a few weeks and a few tasks to program on my own that I fully understand what happens there.
Okay. If there are no questions, I think we can...
Yeah, I think we have a quiz again on the next slide. And it's again a very interesting one. So let's see if there were no questions. So hopefully everybody understood it, and let's see what's the output there. So we have 2 different prints of our data array here. Basically, it's just one missing parenthesis.
Yeah, exactly. But again, it looks dangerous to have the asterisk outside of the parenthesis and here next to the variable. But let's see.
If you followed the practicals, you saw something very, very similar, I think.
Yeah. You've also heard about operator precedence. Let's see. Let's wait a few more seconds.
Can you reach the 50? One more. Yeah, great.
Perfect. Okay,
We've done it.
perfect.
Yeah,
Great.
very good.
That's really great. Didn't expect that,
No,
to be honest.
I'm impressed. I'm
yeah.
very impressed. Very good. So the answer is 10 and 93. Let's go back. Why?
Yeah, I think we have a slide for this. If I'm,
We don't have one. Do we?
yeah, we do.
Ah, we
So,
do. Sorry, I was wrong.
So there we have one with the two different, let's say operations here. So in the first case, we have the dereference of data plus 3. And here we dereference data and add 3.
Yeah.
So what happens in the first example here is we add 3 to the data variable, which means we add 3 times 4 bytes to the address of the first element. So we are here at the first element, position 0, 1, 2, 3. And we have the address here and dereference this address, and this results in 10. So it's the fourth element in the array. And in the second example, we first dereference data. So we dereference the address at the first position in the array, so the zeroth element. And we have 90 then here, if we dereference just data. And 90 plus 3 is 93, and that's why this results in 10, and this here results in 93. But it's really great that so many of you got it correct.
I think we have one more in a few slides, which is a bit more trickier.
Okay, yeah.
But we also have some special pointers left. One of the special pointers, let's call it special, it's the so-called NULL-Pointer. And NULL-Pointer just means it points to null, so you give a pointer the value null. Why should I use that? Some functions will return null if something bad happens. For example, if it doesn't work what the function should do, and it should return you a pointer. Sometimes it returns you a pointer, but in the case that there is a problem, it can return you null, and you can then catch this return value and make an if statement. If this value is null, then I know something bad happens and I can react on that. So again, next week we will see a lot of functions with dynamic memory that actually returns null if a problem occurs. And in this case, then you have this null pointer. I know in this very, very basic example, it does not really make sense to use null, but sometimes it is very useful for special cases that are not the usual case. Yeah.
And you can just use it's not really a keyword, but it's a macro, nar, and you can use it without including any library. So
it is basically the same as you would write the digit null, but it's a bit more readable, and it's common practice to use it with pointers in C. The second one is a bit trickier. The second, so we could also have pointers. Pointers are scary when I heard of that first time. But we had this problem that we have a pointer which has a value of, the value of the pointer is the address of this variable where now I have my value. So this is basically where I have my variable, it's 42. I take the address, store it in a pointer, and then print out the address of a pointer. So basically this one here. And now the question might come, can we store it again? Yes, of course we can. We can create another variable, let's call it pointer2, which takes the address of this pointer as value. And you really write it like this. You create a pointer variable. And when you print it out, it prints actually the value. And the value is, now it's getting confusing.
Yeah.
The value is the address of the pointer, which value is the address of the my variable, which value is 42. And you might expect it, you can add it once more. You can have a triple pointer. You can play it until infinity, basically.
Yeah.
So just to make it clear, pointer is just a pointer that points to a pointer.
Yeah.
Yeah. And you can access it once again.
Yeah.
So
you can do some basic pointer arithmetic again. You can dereference the pointer and again dereference it. So
you're going like from here to
Yeah.
here to here to here to the value.
exactly, if we dereference it twice, then we have the value 42 and we can do some kind of operation here. In this case, we just add 1. We increment it by 1. And if you want to print it, we again have to dereference it twice, and then we can just access the original value of, or in this case, the modified value of my variable.
I have a question to you. What do you think is the size of this pointer? Yes? 8, yeah. It's basically just a pointer, which points again to a pointer, but it's not 16, which you might think of. It's just a pointer, and the pointer is always 8-byte on a 64-bit system.
Yes.
Any questions to pointers? Yes.
You will probably see it in the weekly exercises. There are some cases. For instance, there we have a two-dimensional array, or let's say we have an array of pointers.
Yeah.
So you will get familiar and you will, maybe use it. There are some use cases.
Sometimes you want to hand over the address of an array to a function, and then you need to take a pointer, because the address of an array is a pointer to a pointer.
Yeah.
That's one use case.
Any other questions?
Yes.
Two-dimensional array is also pointer to pointer?
Yes. Two-dimensional arrays. So you can think of this brackets. It's just 1 times dereferencing. And if you have a two-dimensional, you have 2 of these brackets. And this means you are dereferencing twice, which is similar to a pointer.
Yeah.
We say it's similar. It's not on a memory level. No. It's not similar, not really, because the dereferencing is not really an address there, but it behaves completely the same.
Yeah.
So you can use it like that. It behaves the same, but under the hood, on the memory, internally, it works a bit different, but we will have a look at it next week.
Yeah. Exactly. Okay, any other questions before we continue with an array of pointers?
Oh yeah.
Cool.
So we saw pointers, we saw single pointers. We could also make an array of pointers. So basically an array where we store not values, but pointers. And now we have this last Slido question, I think. It's the last one, yeah. So what do you think? We have a struct here with a student. Each student has a name with a fixed size 28-byte and a grade, just an integer. And then we create here an array of student pointers with the size 10, so 10 elements inside. The question is, what's the size of it? And we create a second one, a second array with 10 elements with students inside, and we want to know the size of this one here.
So we've seen that if we have an integer array with 5 elements, we know it's 5 times 4 bytes. So an integer array with 5 elements would be then 20 bytes. And now we are interested in the size of an array that contains or can contain 10 elements which are of type student pointer and 10 elements of type student. So, what do you think is the size of the student pointer array and the student array?
I think our questions are always the same. We're comparing pointers with elements.
Yeah.
And the size of it. But as you might can see, it's very important that you know the differences between pointers and actual, in this case, student objects. So there is, of course, difference. And we want to highlight it 1 times more than 1 times less.
Yeah. It's really important, so it's good to have a look at it one more time. Okay, should we?
Yeah, I think we should continue because we have one more topic left.
So let's see.
Oh, yeah, very
Again,
cool.
great.
It is 80 and 320. That looks odd.
It looks odd, yeah?
But why? Let's have a look at it. So the size of a struct is always the sum of all individual elements inside, so the members, yeah? So we know this one has a size of 28, this one has a size of 4, so the size in general of a student is 32. Okay, so let's have a look at the second one first, because it's a bit more easier, I think. We have a student, class 2, with 10 elements, so we calculate 28 for the name, 4 for the grade, so is 32 bytes. 32 bytes times 10 elements, we end up with 320 bytes. That's why we have 320 in the end. The other one is a bit more trickier, let's say, because it's an array of pointers, but it does not matter what type of pointers. A pointer is, I think that should be the motto for today's lecture, a pointer is always 8 byte. It, regardless of it's an integer, a student or whatever.
Or character pointer, so it's always.
So we just calculate 8 times 10 for the elements and we end up with 80 bytes. That's why the output is here, 80 and 320.
Yeah.
We will talk about structs and size of and pointers in the next and in 3 weeks, then. Yeah. So you will see that a lot in the upcoming lectures too. Okay, I think we are mostly done for today, but we have one more important topic which you also need for assignment 2 and for the weekly exercises, and it's command line arguments. Not really related to topic, but we need topics for that.
Yeah.
You know, hopefully know that we can compile a program like that. Use clang -v also to enable all the warnings, get my output, and then add my C code. So this will compile it. And this is the command, and these are the so-called arguments when I call my program. So what I can do is, when I execute my program, I call it like this, and I can add additional arguments, not only to like inside the program to functions, but also to the program itself. So I can, call my program with, for example, different digits as arguments. So, you can give additional information as parameters to the program.
So, just a quick question. How many of you, just raise your hand, have seen the
this one?
function definition, so the function header like this? So
Like this, yeah.
int main, int argc.
Yeah.
Okay. say half.
Yeah.
So
It's very common.
it's very common. Yeah.
This is the other way. Usually we wrote it like that.
Yeah.
This just means we're taking no arguments when we're calling the program. And this means we want to take arguments. You don't need to take them, you don't need to process them. But if you want, it's a possibility for you. So the main function now can have non-parameter, or it could have two parameters. The first one is the number of arguments you're getting. So in this case, it's 1, 2, 3, 4, 5, 6. 6
Another one. But
plus another one,
we'll
exactly,
see
yeah.
it. Yeah.
And the second one is, oh, what's that? That's an array of character pointers. So it's basically an array of strings.
Yeah.
But we don't know how many it is, because as soon as we are in a function, it's always 8 byte. That's why we need a counter, how many are inside.
So yeah, and if we now have this example here, we call the program using the arguments 4, 6, and hello. So we have 3 additional parameters. And when we now print these parameters or these arguments here, we will get 4 arguments. Why do we have 4 arguments when we only passed 3?
So we pass 4, 6, and hello.
And
So you can see you can mix it up. You can have integers, you can have strings, whatever.
Yeah.
But the zeroth argument, the very first one, is always the program call itself.
So if we call the program my program, and then we have the element at position 0, it's really the calling of the program as you do it in the terminal or wherever. And yeah, you can use additional arguments here. They are all stored as strings. So if you pass, for example, 4 as a parameter, it is stored as a string as 4. So you cannot use it, for example, to add 2 numbers or add this parameter to something. So what do we have to do if we want to use, for example, an integer value?
I will come to that shortly.
We'll see that, yeah.
But first, as you have seen before, it's very common to write it like that in the beginning of the main if you know your function should work with command line arguments. As we have seen today, use this guard clause syntax or framework, let's call it like that, and just exclude everything that has not the correct number of parameters. So in this case, I know my program always needs to have 2 or 3 or 4 parameters, whatever, and I exclude all of them which are less than 2. I could also write it should be exactly 4, for example, it should be exactly 7, I don't know. And in every other case, and this is also what you should do in the assignments, you should return in a specific with a specified return code. In this case, it's 1. But it's declared in the assignment description. But as you said before, we always get back the values, so the arguments, as strings. So all arguments are strings. We want to convert it to an integer.
In this case, an integer, yeah.
And there are possibilities in this standard lib header library. For example, the atoy function, which converts a string to an integer, you can just call it like that. Or the atof function, which converts a string to a float. So, oh, I'm sorry, this is a copy-paste. It should be float here. Or what we would recommend is the strutol function. It converts a string to a long integer, so you get a long back, but it also includes some error handling. And that's because you have another pointer there. So you have to give the address of a pointer as parameter, and it kind of indicates you if there's a problem or if the string is empty or out or over. And the last argument here just means base 10, so you want to have it in decimal. You could also have it, for example, in hexadecimal, but in most cases I think this is sufficient to get a decimal number back. All right, any questions to this? If you want to know how Strudel works, I think you also have to do it for the assignment. Just Google it, ask ChatGPT or whatever. There's a lot of documentation how this works and examples how this works. Any questions to command line arguments? Yes?
So this pointer operator and we have to actually set the next argument.
It's automatically set. So it's automatically set. You really just have to write it like this. Create a pointer and give the address to this pointer. It takes a pointer and it will store the value or the next, it's a bit complicated, next character after the integer, for example, you want to read. Yeah, and if there is nothing behind, it's null. So you get to return a null pointer. If there is something behind, you might have 2 or 3 numbers in a string you want to get out of the string, and then you have like a pointer to the next beginning of the next integer. This is basically what it's stored there. But I know it's a bit complicated. Just see a few examples, and then it should be easier to understand.
And also trying out stuff.
Yeah.
So you can also use online GDP to pass command line arguments, and you can just try to work with command line arguments. Also converting it to int and floats. But you will need it anyway for assignment 2.
All right, if there are no more questions, then I think we are done for today.
We're done, yeah.
Sorry for the delay, 5 minutes over, but thank you very much.
And see you next week, yeah.